Suppose you have a function that seems continuous except for a hole in it, and you want to know what the value of the function would be if the hole weren't there. A reasonable way to do this qualitatively would be to check the value of the function closer and closer to the hole to figure out what the value of the function might be in the hole itself. We have devised a rigorous mathematical process to do this. Suppose that this hole occurs at the location x0, and that our proposed limit has the value f0. We will create a variable called epsilon, which describes how close a function value is to the limit f0. We will also create a variable called delta, which describes how close an x value is to the limit x point x0. The point of an epsilon delta proof is to show that we can get arbitrarily close to f0, that is, epsilon can get very, very small, and for any epsilon, no matter how small, we can pick a delta such that x points which are within delta of x0 will have function values that are within epsilon of f0. The actual math of this proof goes as follows. This expression is the distance in absolute value between some function value and the value of our limit f0. That is, how far away we are from f0 for a given function value. Suppose we are given some epsilon such that epsilon is greater than 0. We need to find a delta such that when the distance between some value x and the limit point x0 is less than delta and greater than 0, then this statement is always true. That is, for any x that's in a certain range delta of x0, the values of the function for that x will be in the epsilon range of f0. To accomplish this proof, we typically need to rewrite this expression so that it is in terms of this expression and is therefore less than some multiple or power or whatever of delta, and then epsilon can become related to that delta. This works for complex numbers as well. We need to replace x with z and x0 with z0, and everything should still work. As an example, let's consider the function f of z equals 2z, and we want to know the limit of this function as z approaches 1 plus I. Obviously, the limit of this function is equal to 2 plus 2i, but we need to prove it using an epsilon delta proof. So we need to show that f of z minus 2 plus 2i is less than epsilon whenever z minus 1 plus I is less than delta and greater than 0. To do so, let's rewrite this expression fz as 2z and write 2z minus 2 plus 2i and find out what this expression is less than. We can factor out 2 to get z minus 1 plus I, and we know that z minus 1 plus I is less than delta, so this must be less than 2 delta. We also know that it needs to be less than epsilon, so if we set epsilon equals 2 delta, or delta equals epsilon over 2, then because 2 times z minus 1 plus I is always less than 2 delta, this thing, which is exactly equal to this thing, will always be less than epsilon as long as delta equals epsilon over 2. There are a couple other principles you need to perform epsilon delta proofs in the complex plane. The first of this is to consider the implications of this fact that z minus the limit value is less than delta in terms of the x and y components and the triangle inequality. I'm going to do this in blue. Z minus 1 plus I is also the same as x plus iy minus 1 plus I. And that can be written as x minus 1 plus I y minus 1. And this is less than delta. Now, based on the triangle inequality, the magnitude of x minus 1 is less than the magnitude of z minus 1 plus I. So is the magnitude of y minus 1. Y minus 1 is less than z minus I plus 1, and thus it's less than delta. Both x minus 1 and y minus 1, when you take their absolute values, are less than delta. To practice this, let's redo our proof and rewrite this function. F of z minus z plus 2i can be written as 2z minus 2 plus 2i, and z can be written as x plus iy, and this can be rearranged into 2x minus 2 plus I 2y minus 2, which by the triangle inequality is less than 2x minus 2 plus 2y minus 2. We can factor out 2 out of both of these terms, and observe that because x minus 1 is less than delta and y minus 1 is less than delta, this is less than 2 delta plus 2 delta, which is less than 4 delta. And since we know that this has to be less than epsilon, we can set 4 delta equals epsilon, or delta equals epsilon over 4. Now, the problem that you have for homework is more complicated than what we did here, but basically it's just going to take you rearranging what you have in the absolute value bars for here in the less than epsilon section until you can get things like z minus z naught in your bars, or x minus x naught in your bars, and then you can split that up using the triangle inequality. You may need to introduce new terms into the absolute value bars by adding and subtracting numbers, like adding 1 and subtracting 1, in order to get things into the right form, but they should always work. Anyway, let me know if you have any other questions.